Hey everyone, geophysicist Stefan Burns here. We now have imagery of interstellar object 3I Atlas as taken from
October 2nd, 2025. The Martian night was supposed to be quiet. Perseverance's sky cameras were running their routine long exposure sweep when something sliced through the starscape. A streak, thin as a filament, moved across the horizon at 60 kilometers per second. The timestamp aligned perfectly with the predicted passage of 3I/ATLAS, the interstellar object now approaching its closest flyby of Mars. For 90 frames, the flash maintained a steady velocity and bearing. No atmospheric scatter, no fading tail, just one pure, linear motion at impossible speed. Within hours, amateur astronomer Stefan Burns noticed the anomaly buried in Perseverance's publicly accessible RAW archive. He downloaded the entire batch, 9 minutes of night sky imaging captured by the rover's micro-navigation cameras. One frame at a time, he aligned them against a fixed star catalog and measured the pixel shift of each light point. Then he found it. A single linear trace cutting through Mars's faint constellations. No flicker, no discontinuity. It moved as though drawn with precision across the sky. Burns applied textbook calibration. He verified timestamps embedded in the metadata, matched stellar separations, and corrected for Mars's axial tilt. Then he plotted the trajectory against the JPL Horizons ephemeris used by NASA to predict 3I/ATLAS's path. The overlay was perfect. The direction, speed, and time aligned down to the second. Whatever the streak was, it matched the incoming interstellar visitor's motion exactly. At Mars's distance from the Sun, natural debris rarely exceeds 10 kilometers per second. Even impactors entering the Martian atmosphere slow quickly due to thin air drag. The Perseverance streak held a consistent 60 kilometers per second, 6 times the escape velocity of Mars, moving parallel to the planet rather than into it. No meteor fits that pattern. No orbiting satellite moves at those speeds. And Perseverance's CCD detectors, hardened against cosmic rays, showed no single pixel spikes typical of radiation hits. Every check failed to debunk it. The images went public within hours. Burns released his 9-minute time-lapse on October 3rd, posting the raw stack and calibration code online. In less than half a day, downloads crossed 40,000. Independent analysts across continents began stacking the same frames, writing new scripts, running alternate noise filters. Forums overflowed with plots and overlays, each trying to replicate or refute the finding. The Martian sky, once a backdrop of quiet stars, had just become the center of a data storm. The streak ignited global scrutiny. Teams of data analysts and astrophotographers split into factions almost instantly. One group confirmed Burns's measurements, reproducing the 60 kilometers per second track using independent photometric calibration. Others dismissed it as overfitted noise, a product of cosmic ray interference stacked too aggressively. Both sides had math. Both had confidence. Neither had the missing link, raw telemetry. Then came the green flash. At exactly 0003 UTC, several independent reconstructions displayed a faint emerald emission lasting less than 1 frame. To some, it looked like a chemical outburst, a plume of excited gas reacting to sunlight. To others, it was nothing more than a misaligned color channel or a high-energy particle strike on the detector. The flash became a fault line in the discussion. Was it a genuine emission from 3I/ATLAS or a digital ghost? The debate intensified when the absence of FITS files and camera logs came to light. Without the raw data from Perseverance's onboard instruments, every analysis was provisional. Frame compression, gain adjustment, and cosmic ray cleaning routines all remained undocumented. Experts demanded transparency. Without full calibration headers, even the best image stacking could not be trusted. Online research hubs fractured overnight. One side, the artifact skeptics, argued that aggressive stacking produced phantom lines, coincidences of noise aligned by wishful scripting. The other side, the signal advocates, pointed to cross-matched timestamps and alignment with the horizon's prediction as evidence too clean to dismiss. They traded arguments over signal-to-noise ratios, plate scale corrections, and cosmic ray rejection algorithms. Each camp posted code, data, and rebuttals in a race to own the narrative. By the morning of October 4th, calls for institutional arbitration flooded social media. Researchers demanded NASA or ESA verification, an official statement clarifying the streak's authenticity. Neither agency responded. JPL issued no updates. The silence stretched while the debate consumed every scientific forum on the web. Behind the noise, another story began to surface. For months, 3 orbiters had been quietly preparing to image 3 I/ATLAS as it crossed Mars's orbital plane, MRO, TGO, and Mars Express. Each had been scheduled to capture the flyby at a staggering 9 million kilometers from Mars, roughly 75 times the Earth-Moon distance. The campaign was ambitious, but risky. At that range, even the most powerful Martian cameras would see 3 I/ATLAS as a speck no larger than a handful of pixels. HiRISE, the sharpest camera in Mars orbit, typically resolves boulders and craters. To capture an interstellar object moving at 58 to 60 kilometers per second, engineers had to rewrite its observation routines entirely. Each exposure became a gamble. Aim too early, and the object would streak out of frame. Aim too late, and it would vanish into the background. At ESA's Cassis instrument aboard the Trace Gas Orbiter, the team prepared a sequence of 4-band exposures designed to detect faint color variations or outgassing jets. Mars Express's HRSC, with its wide swath coverage, was assigned to search for large-scale structure, anything suggesting fragmentation or a multi-body configuration. The window was brief. Each spacecraft had minutes, not hours, to get its data. Every exposure relied on daily horizons updates, refined with each new positional fix from Earth-based tracking arrays. The orbiter teams received those coordinates with just enough lead time to command slews away from their usual nadir pointings. A few degrees off, and they would miss the target completely. With no real-time tracking, every image depended on prediction and timing. When the flyby concluded, the orbiters fell silent. No quick-look images, no uncalibrated frames, no compressed previews reached the public archives. Normally, Mars missions release preliminary data within days. This time, there was nothing. Just terse notes about data processing and ongoing calibration. The absence only fueled speculation. Had the orbiters seen the same streak Perseverance recorded? Did they capture the rumored green flash from a different angle? Or had cosmic radiation flooded the sensors and corrupted the data? Inside JPL, engineers reportedly worked around the clock to reprocess every frame. Registration drift, cosmic ray impacts, and flat field distortions were cross-checked line by line. Each exposure compared against the predicted track to identify any genuine object motion. The workload was immense, but the silence outside made it sound deliberate. The pattern repeated one more time. A public discovery, an unverified anomaly, and then the blackout. Mars had become the solar system's only vantage point on 3 I/ATLAS during its closest pass. For a few hours, every instrument aimed into the void at the same coordinates. One streak, one flash, and a world now waiting for confirmation. If you're tracking this investigation as it unfolds, hit subscribe right now. Every update from Mars orbiters, every decoded spectrum, every recovered frame will land here first. And if you want these reports to reach others watching this story unfold, tap like. Because whatever's crossing our skies tonight, the data trail is already rewriting what we know about interstellar visitors. Mars archives stayed empty long after they were supposed to open. Normally, uncalibrated orbiter data appears within 3 to 5 days of downlink. For headline events, agencies even release quick-look previews. But October passed with nothing. No images from HiRISE, no color composites from CASSIS, no wide-angle scans from HRSC. The servers stayed blank. The silence was total. Inside JPL, the official explanation pointed to contamination. Engineers cited cosmic ray interference and registration drift as the twin causes of delay. Radiation storms near the sun had peppered every sensor with false streaks. Some frames were riddled with pixel spikes mimicking motion trails. The calibration pipeline wasn't designed for that level of noise, so the team shut it down and moved to manual review. Every image now had to be inspected line by line. If you want every new update the moment the Mars data drops, hit subscribe right now. And tap like so this story reaches others following the trail. Because the next frame we receive from that silent corridor between Mars and the Sun may decide whether 3I/ATLAS is a cosmic relic, a natural outlier, or the first engineered traveler ever caught by human instruments. Each frame was compared against the Horizon's ephemeris that predicted 3I/ATLAS's path. Analysts cross-checked every predicted coordinate against the actual pixel trail. If the light trace fell even 1 degree off, it was flagged. The goal was to ensure that no cosmic ray artifact could masquerade as a fragment or companion object. The validation process slowed to a crawl. Days turned to weeks. The data bottleneck became visible from the outside. Observers noted a strange paradox. Transparency always vanished when anomalies appeared. When 3I/ATLAS showed nothing unusual, images flowed freely. When it broke the rules, like the green flash or the plasma reversal, the data froze behind review walls. The timing couldn't be ignored. The community called it coincidence. The pattern suggested control. Inside the calibration rooms, the tension was clear. Released too early, and a misaligned stack could trigger global panic. Wait too long and suspicion would explode. The imaging teams walked a tightrope between precision and secrecy. Multiple engineers admitted privately that it wasn't about hiding data, it was about surviving interpretation. A wrong pixel could reshape the story. Teams at HiRISE, CASSIS, and HRSC kept recalibrating cosmic ray rejection filters. Algorithms tuned for Martian landscapes failed to recognize linear motion from a 60 kilometers per second interstellar object. Every fix required new scripts. Every script risked wiping faint features. Each decision balanced accuracy against time. The longer the silence lasted, the louder the theories grew. By mid-October, Mars Express finally uploaded partial spectra, and what they showed didn't make sense. The nickel lines in 3I/ATLAS's reflected light were stronger than iron, an inversion of every known cometary pattern. Planetary chemists ran the ratios again, thinking it was a sensor misread. It wasn't. The nickel abundance dominated across multiple wavelength bands, verified by both HRSC and CASSIS instruments. Then came the gas data. The trace gas orbiter recorded carbon dioxide outgassing 10 times stronger than water vapor. In any ordinary comet, Water drives the jets as the nucleus heats up. Here, water barely registered. The CO2 plume dominated, releasing energy levels too stable for ice sublimation alone. Standard comet models broke instantly. Imaging analysis added another shock. Instead of trailing dust away from the sun, three I/ATLAS's main jet shot forward, a sunward anti-tail, bright and sharply defined. Dust simulations couldn't reproduce the shape. For the plume to hold that direction, the nucleus had to be rotating under some form of active stabilization. Only a massive core could survive the force without spinning apart. Orbital data placed its minimum mass near 10 billion tons, more asteroid than comet. The color bands deepened the mystery. Reports of a green flash had implied dicarbon emission, the chemical fingerprint of carbon chains breaking under sunlight. But the C2 SWAN bands at 516 and 563 nanometers were missing. The green existed, but the chemistry to create it didn't. Laboratory physicists called it a paradox, a color without the molecule that makes it. Either another unknown compound emitted at those wavelengths, or the glow was not chemical at all. Spectroscopists kept repeating the same phrase: chemistry without precedent. Every ratio, nickel to iron, CO2 to water, emission to absorption, broke the textbook order. Even the spectral lines carried micro-oscillations inconsistent with thermal broadening, as if modulated by an external field. Theories scattered. Synthetic contamination from spacecraft exhaust, embedded nanostructures altering photon scattering, or an entirely new class of matter. None fit cleanly. The pattern was structured, yet non-random. It looked engineered. Then a new thread emerged. Researcher Avibe and his team began orbital backtracking to test whether three I/ATLAS's trajectory ever intersected known radio anomalies. Using decades of JPL Horizons data, they projected its hyperbolic path backward across the celestial sphere. The result startled even them. The trajectory passed within half a degree of the coordinates of the 1977 WOW signal, the famous narrowband burst detected at 1420 MHz, the hydrogen line. The chance of such an overlap was small, about 0.6%, but not impossible. SETI analysts called it an alignment worth investigating. Skeptics called it coincidence dressed as revelation. The hydrogen line frequency holds special weight because it represents the universal constant most likely to attract attention across civilizations. A craft crossing that coordinate during a high-energy burst invites speculation, but science demands replication. Regardless of interpretation, the coincidence reignited public attention. SETI arrays in Australia, Spain, and Puerto Rico began monitoring 1420 MHz continuously. No signals emerged, but the idea refused to die. Every mention of the WOW signal carried a cultural gravity of its own. Linking it to three I/ATLAS turned an astronomical anomaly into a global mystery. Then came the blackout. After October 29th, three I/ATLAS moved behind the Sun. For the next 5 weeks, the object would be invisible to both Earth and Mars-based instruments. The glare of the solar corona created a blind zone extending millions of kilometers. Spacecraft safety protocols forced every telescope offline. The most watched object in the solar system vanished.